What happened?
The base attacked the ring with the two oxygens. You got maybe a negative there, so it attached to the main structure, water structure.
So in your approach to answering my question of what happened, were you processing all the steps that you knew needed to happen to get to this point, or were you just saying what happened as a difference?
I would say it's the only kind of makes, because there are different, I mean, the base is the most, so the charge, it's going to be the most reactive.
So looking at the base, most reactive, I can agree with that.
So you wanting to look at for any hydrogens that could be attacked by the base.
There it goes. So when I said what happened, what you started to do was look only at your reactants and said what could possibly occur. Okay. I'm not saying that's wrong. Okay, but before even launching into that, I would argue we've got an easier step. What we should be doing is looking at reactants to products and saying, where do we see a change? Say again? Pi bond next to the carbonyl, what about it? It's not in the product, so I'm losing a pi bond. Okay, if we're following that logic out also, we might go through and say that we lost a hydrogen. So that bond is lost. That one becomes a much harder bond, in my opinion, to see because you'd have to actually identify that change. So we've got a loss of a pi bond, we've got a loss of that hydrogen. Anything else happened? Argue there's a pretty big one. What's that? The ethyl part didn't actually change. So we've got CH3, CH2 carbon, CH3, CH2 carbon. So I would argue there's no change there. I started with two things, I end with one thing. That's a pretty big flipping difference. Okay? So where is that new connection? Okay. So we're talking about there. Kind of makes sense? What kind of chemical reaction do you think we're doing? Okay, if we do an elimination, what's the natural byproduct of the elimination? How do you know you've done an elimination? Describe elimination.
Something's missing, like something's missing.
And so the something that's missing isn't a bad phrasing necessarily, but unfortunately we have to be really, really clear behind that because depending on how you look at your reaction, you will always have something missing. No. Okay, we broke a pi bond. So when we talk about an elimination, okay, if we combine your two thoughts, something is missing and you're saying broke a pi bond. So if I do an elimination, that means loss of a pi bond. Is that true? No. An elimination is the formation of a pi bond. So it's not an elimination reaction. Yes, something is missing, but again, how we quantify that what is missing becomes the problem. Okay? In this case, we've lost a pi bond. What chemical reaction resulted from a loss of a pi bond? I mean, does it say addition? I mean, it does kind of at the top. Here, I'll make you feel better. Okay, so we are looking at an addition reaction. What kind of addition? What things were added when we did this reaction? So if we consider an addition, it is the loss of a pi bond by doing what? That's now saying a nucleophile addition. We could do an electrophile addition. So just an addition generally. What happens? It's the loss of the pi bond by doing what? So if I said substitution, what would a substitution be? Loss of a leaving group, gain of a nucleophile. Right? So what's an addition? Loss of the pi bond and gain of 2 sigma bonds. If we go through and look at this product, have you gained 2 sigma bonds? Yeah? I mean, what I've identified so far is just 1 sigma bond.
There's 100 here.
Oh, okay. Right? So we have the loss of a pi bond, and we have the gain of 2 sigma bonds. Right? So now we want to kind of push into the language game behind this to kind of evaluate what's going on with some of these additions. Okay? If we look at those 2 new bonds, they are spaced exactly 1 bond away from each other, so we might reference this as position 1 and position 2. Position 1 and position 2 are completely arbitrary, made-up numbers. Okay? They're just distance locations, that's it. So it's not nomenclature. So we might go through and say, well, I added things at position 1 and 2. Wouldn't this be a 1-2 addition? Okay? Unfortunately not. What kind of an addition is it? It's a 1-4. So now the fun question, how do we know it's a 1-4 addition, sometimes known as conjugate addition? When we go through and look at those products, what would give us that tip-off?
So, I mean, we can probably go back to the other thing that's being attached to it, right?
Okay.
And you can see that, if a base attacks that hydrogen there, we get a negative carbon, and a negative carbon would indicate that we're I forgot the rules, but isn't it oxygen that
Okay, so I think I like where you're potentially going with that. So what you're doing is now going back through where you initially wanted to start, and then I made you not do that.
yeah, thank you.
You're welcome. Okay, was looking at those individual pieces and saying, okay, how did the chemistry actually happen? Okay, so I flipped the entire script and said, let's go through the name effective route behind this. Because we're going to be looking, you look at both of those pieces, right? Some people are memorizing things, some people aren't. Okay, so if you're just following the chemistry, we don't necessarily care that it's a 1-4 or 1-2 as long as we follow the process right, which is what I think you're leaning into. So that's good. Okay, but if you're going to go through and memorize, you're going to be real careful. Because if we label this out, this is a 1-4 conjugate addition, but it sure looks like a 1-2. Okay? The end result here looks like a 1-2. So what's going on? Well, if we go back to what he's asking about or pointing out, we've got that negative carbon. What does the negative carbon need to react with?
Positive.
A positive. Where are their positives?
And the pi bonds and the main structure.
Okay, so we go hydrogen, that's acid-base chemistry. That just undoes what we just did. The carbonyl carbon, okay, arguably that's the largest positive. Why is that the largest positive? It's closest to the electronegative oxygen. Fantastic. Okay, is that where we had our nucleophile attack? No. Okay, where did our nucleophile attack then? Okay, so I like this because you've got the chemistry and you're just trying to make up the numbers to kind of fit along.
One starts in oxygen, right?
Kind of arbitrary. I honestly don't know necessarily where the 1 starts. Okay, if we go through and number that out the way he's suggesting, again, not necessarily wrong, but potentially misguided. Okay, That 4 position is also partially positive. Why? There's a resonance within the system, which means we get 2 possible positives that can go through and react. So when we talk about the reactivity, when we're talking about 1,2 versus 1,4, we're saying, where did our nucleophile react? Does it do a nucleophile attack at position 2, where we've defined the oxygen as position 1, or does it attack at position 4 relative to the oxygen? Okay. Even then, if you look at the end result, it doesn't look like 1,2 versus 1,4, and that's because if we look at the 1,4 addition, would have been nice if I picked a smaller structure. What does our initial product look like? When we talk about the 1,4 addition, our nucleophile comes in, attacks what we're labeling as position 4. The extra sigma bond is our hydrogen, which then goes to our oxygen. That's the true 1,4 addition product. What happens to this product? Why is that not the product we actually drew? It has to do with that functional group. That functional group is an enol, and enols quickly tautomerize. So we form our initial nucleophile addition product as a 1,4 or as a 1,2. That product, in the case of the 1,4, quickly changes its configuration out to look like the official product. So the 1,4 conjugate addition is hidden behind some secondary chemistry. Okay? So I want you to be aware that if you're seeing 1,4, it is still technically a 1,4 addition, even though the end result looks like an arbitrary 1,2. Kind of make sense? What we're trying to, again, walk through are just the major changes that are happening behind it. We haven't pushed any of the mechanism behind how we got to this product, because ultimately we should have done that mechanism at the end of last week. That was Thursday's class. We should have gotten to this 1,4 conjugate addition product. Okay, and what's exciting about that? It's not the correct answer for the question. We have to continue onwards. So what do you need to do? It's not a bad idea, silence. Hope someone steps in and helps you out. You can get up and go to the boards, and you can continue this reaction. Yep, that's what I said. Get up and go to the boards and continue the reaction through. It does not stop, it must continue. So figure out how it continues. Number 1, it's called a Robinson annulation. It's a famous named reaction, and potentially one of the reasons it's named is that if we look at the scaffold behind, there's a lot of different moving parts and pieces going with it. So first and foremost, it starts off with that 1,4 conjugate addition. So we would get our 1,4 conjugate addition. Oh, okay, now we're done. Okay? And potentially, maybe when Robinson's group tried to run this reaction, they thought it would be done, and then it continued. Okay? So they mixed all the reagents together. They looked at their final product, and their final product was not this. So they had to come up with a reason for why it became something else. Okay? They had a little bit of leverage that we don't have because they probably had the official structure of the product. Okay, so what I was trying to make you do is push at what are the possible things that this could continue with. Okay, in the presence of KOH, what we're going to be concerned about is all of our alpha hydrogens. Okay, our alpha position is right next door to the carbonyl. So I have an alpha position noted there in red. I also have an alpha position at the other side of it. Okay? Those alpha positions we could deprotonate and then make nucleophiles. Would they be negative carbons? Okay? If we continue through the structure, we should see we have an alpha position there. Okay? And we have an alpha position there. Okay? Arguably, we have one up here also, but that's going to be identical to the bottom one because of the line of symmetry, so I would argue we could ignore that and not have stress about it. Once we have those as negatives, they need to find something positive. So I got a lot of people saying for that red alpha position, oh, there's a positive right next to it. Okay, that's good. Okay, you're acknowledging that positive because of resonance within that. That resonance isn't going to change the structure. It's not a permanent way to stabilize it. So that positive isn't a particularly useful one to look at. Okay, and then we encountered kind of the next tripping stone block. Is everybody, well, I don't see any other positives. Okay. The positive you picked was because it was next to an oxygen. There are other carbonyls that are equally positive. Okay? So I could take the electrons once I've deprotonated it and share it all the way across. Okay? And this usually brings up two big common questions. One, that is so far away. How could it possibly happen? Okay? It's really not that far away. If we look at that group out here, that's all single bonds. Those single bonds can freely rotate, spin, flip, and move. And so if we redraw the structure, which is going to take me a second, and you'll note that I'm stuttering here, but I'm going to attempt to do it correctly. Okay, there's our alpha position. There's our positive, so we're taking the electrons and going right there. Those are right next to each other. Distance-wise, that's very, 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 very close. But because of how we chose to draw the product of the 1,4 addition, we have hidden the ability to do this step of the reaction, which would be an intramolecular addition. Okay? And it's that step that becomes kind of tricky and trips people up. Okay? And arguably, it was not seen, I would bet it was not seen by Robinson's group when they went through and did it. Okay? It was only after the fact when they had the clarity of the product to go, oh, what had to have happened? Okay? And because they then went through and said what had to have happened, they can go through and now name it, and everybody knows it as this famous reaction. Kind of makes sense? Okay. In drawing out that flipped chain, okay, even within the video, and maybe if you were watching my face while I was trying to draw it, I was struggling to actually get that to identify, okay, to get all the carbons aligned right. Okay, and that is absolutely a challenging thing to go through and do. So for all of these types of reactions, be it Robinson, 1,4 conjugate additions, or when we push on this a little bit more, the aldol reactions, you should be very careful to count your carbons. Okay? That counting of carbons is going to help you to close the loop and make sure that you've got this set up correctly. Okay? I would argue more than likely what you'd be seeing is the thing given initially. If we're looking at our chemistry, we're looking at connecting position 1, 2, 3, 4, come on, 5, 6. Which means when I go through to draw out my product, I'm 1, 2, 3, 4, 5, 6. If I'm going to draw out my formal product, I'm forming a 6-membered ring, which I'll color in blue. 1, 2, 3, 4, 5, 6. Okay, that red ring connected out. There's my carbonyl. I would then put my kind of substituents, which I'll show as a separate color, on at those other positions. Okay, if I'm going to be a little bit more careful with my arrows, okay, when that nucleophile came in and attacked, it breaks the pi bond, which means I have a single bond to my O negative there. So counting those carbons can allow me to build that structure out better than just trying to eyeball it. Because if I eyeball it, more than likely I'm going to drop at least one carbon, if not more. Kind of make sense? Right? You're not graded, and even if you were graded on the prettiness of your picture, okay, those numbers can be erased after the fact if you really wanted to. Okay? I don't care. If I'm going to ask you this for drawing it out, I would expect to see numbers on there because I know it's difficult to draw those things out. When these things get published, we don't put those numbers on there because it makes it look ugly. It goes, oh, you're making something look stupid. Well, yeah, but it's the process by which we're able to account for all of our individual structures. Kind of make sense? Hi. If we double back to the initial question was, I said there are 4 products. We just drew one. Okay, so if we go back to our alpha hydrogens, we had that blue alpha hydrogen. That blue alpha hydrogen can again do resonance to the carbonyl at what I've numbered carbon 5. Again, not useful. That's just looking at resonance. I want to look at chemistry. I could have it go through and react with that carbonyl. Okay. Is that going to change my output? Well, how would I do it? I know that black ring didn't change. The other carbonyl didn't change. That top one is going to change. That's going to become my negative. If we're going to go through a number, 1, 2, carbon 3, carbon 4 is connected. And I go, oh, well, that looks pretty ugly. But if I'd slowed down just a little bit and said I'm connecting carbon 1 to carbon 4 with just 2 other atoms in between, that would be known as what kind of a structure? A cyclobutane. And I could just draw it as a square and make it look real pretty right out of the gate. Okay, 3, 4. Again, I'd want to deal with all those little hangers on. At position 3, I have my ethyl. Position 4 is going to continue off to give me position 5 with my carbonyl, position 6, and then my phenyl. Kind of makes sense? So what you're trying to do is recognize where all of those things can react. I'm not going to draw out the purple or orange one. Okay, I'll leave you guys to look at the boards for that one. I'll point them out here in a second. But let's just look at the 2 products that we've started to draw out, or that we've got drawn here. I'm going to regret erasing that. Both of those are possible conclusions of this reaction. Are they both equally likely? No. Okay, well, this 1, 4, that should be closer, right? Distance-wise, that's only 4 carbons. So that should be a whole lot closer than this one with 6 carbons. Except, to get 4 carbons close, you're going to have to shrink down that bond angle, and there's a lot of stress behind it. That's not an easy bond angle to close. Which means, if we count numbers of carbon, it appears closer, but that's like trying to get your hand to touch your elbow. Okay? I can go to my head, it's further away distance-wise, but that's an easier angle to close. Does that make sense? So what we're relying on there is back to OChem 1, 6-membered rings are more stable than 4-membered rings. If I've got an opportunity to make that 6-membered ring, I'm going to make it. Okay? When I make that or close that out, I then have that negative oxygen. I can stabilize that negative oxygen by picking up a hydrogen from the solvent, our water. And we say, okay, are we done? Okay. At this point in the reaction, if we tried to actually piece together what chemistry happened there, I would argue the chemistry that happened there is aldol. What did aldol stand for? Aldehyde and alcohol. So that when we reacted an aldehyde with itself, with 2 molecules of aldehyde, okay, we have an alpha hydrogen in one position. That alpha hydrogen gets deprotonated, attacks the other aldehyde. We turn that aldehyde into an alcohol. And so the end structure is an aldehyde and an alcohol. We don't have an aldehyde here, but the chemistry associated with that ties back to that alpha position, alpha to the carbonyl. This is aldol chemistry, though it's not an aldehyde specifically. Does that kind of make sense? When we talk through the aldol chemistry, typically we don't end with the aldol product. Instead, what do we end with? An elimination. Okay? And that elimination has a lot to do with the fact that there are still alpha hydrogens that are acidic. Since those alpha hydrogens are acidic, we could remove that alpha hydrogen, making it negative. The electrons could shuttle in to kick out the OH as a leaving group. Okay? Deciding which alpha hydrogen to remove does become a challenge, and I had not actually factored that into the number of possible products. I should color code that differently. We'll call it orange. Our orange alpha hydrogen can be removed by the base, shuttle the electrons in, and we kick out hydroxide as a leaving group. Is hydroxide a good leaving group? No, it's a horrible leaving group, but what are we leaving into? A basic environment. So relatively speaking, it's fine. Okay? So we have to remember that context, particularly as we're looking at our aldol reactions. Okay? What kind of chemical reaction are we doing here? It's not going to formally be an acid-base, even though we've lost an H+. It's an elimination because what formed? We form a pi bond in our product. As I'm trying to quickly draw out the rest of the structure. If we've now formed a pi bond, we've done an elimination reaction. So when we talk about aldol reactions, very typically they're referred to as aldol condensation. Why do we call them condensation? When we eliminated, what did we eliminate from the molecule? OH negative and H plus, formerly H2O. So whenever we run these condensation reactions, okay, they were typically done with alcohol leaving groups or OH leaving groups, and when we ran the reaction with heat, we would see a condensation ring form within our reaction. Why? Because we're eliminating water. And because we've provided heat, that water turns into a gas and we see that condensation ring. That's why it's called condensation. Okay? It's a name strictly from the observation of the chemical reaction. There are lots of reactions that can be called condensations. In fact, every elimination reaction can be called a condensation because you are eliminating something. They shouldn't all be called condensation because of the origin of the name. Okay? So why does Robinson get to attach a big name to this? Well, first it did a 1,4 conjugate addition. Okay? I believe technically known as a Michael addition. Why did we name that? Good question. I think naming all of these was fucking stupid because it's all doing the exact same chemistry. Okay, so we've got a Michael addition followed by an aldol followed by a condensation. You've strung together 3 independent major reactions into one cycle. That's a pretty good argument to say you deserve to name that reaction. Kind of make sense? Okay. Good work, by the way.
So I'm just not work for this one, because I said to just draw the constructed product. Is it asking for this one because it's the most likely, or for any product?
Yes. So if we go around, I think you guys have the most over here. Because you do 2 possibles here. So if we ignore, I'm just going to erase that one. So if we take a look what the group did over here, then I erase some of their work. We've got the primary product. Okay, they eliminated slightly differently than I did, and phenyl groups are in different spots. So I may have bollocks to where the phenyl group is, or you guys did. So pay attention to that. But we've got the primary focal group where we have our 2 6-membered rings next to each other. We've got the possibility for the 4-membered ring, which we deleted from the screen. We've got a possibility for a really gross looking one, which is actually 2 fused 6-membered rings. Okay? Fused in a way where we get a 1-carbon bridge between the 2 rings. Okay? It's really hard to draw. It's really hard to visualize. Okay? To give you an idea, those people in lab, do you remember the Diels-Alder lab?
Mhm.
You remember that structure that you were trying to draw?
Yeah.
That's it. Okay? Except more complicated because in your case, in the Diels-Alder lab, we had 2 5-membered rings. This is 6-membered rings. And then the last one is another 4-membered ring, but it's not the 2 rings fully connected. It's what's known as a spiro. I keep calling it wrong. The spiro compound, and I'm just going to draw a quick, meant to draw an easier example, and I can't figure it out. So we'll do that, 2 5-membered rings. When you've got that position where your 2 rings are connected at a single point, that's known as a spiro. Right? Not a big deal, it's just a name that could pop up. Spiro complexes have interesting properties. Right? So each of those other products all have something bad associated with them, something challenging, which is why we get one major product, which is why Smart Working Array was saying identify the major product. Kind of makes sense?
Is there like a lot of steric hindrance in the one that's the 2 6-membered rings that are really?
I'd have to look at that one a little bit more carefully. It might be sterics. I honestly don't remember off the top of my head. And it may just be having 2 6-membered rings fused like that changes your entropy. You get limited rotation, which is also going to shift away from that as a possible product. Those rings would have to rotate with each other. We're officially done, so I'm going to go ahead and stop. Apologize.